Before we start the lesson for this next unit on vectors, I just want to remind you one of the key and critical items from the entire previous unit on vectors, which was the idea that a vector is a directed line segment. And that means that it has both magnitude, it has a length of the line segment, but it also has a specific direction. Now, one of the things that we did many times in the previous unit was we expressed that vector in R2, which is what we're looking at here. We have the x and the y axes here. We're in R2. We express those vectors in terms of their x components and y components. And you can express that in component form, which is using the brackets, or you can be a little bit more explicit and you can use basis vectors, the ij basis vectors. But these are all equivalent forms, and both this diagram and these two algebraic notations, they mean and they represent the same thing. We're talking about the vector OP in this case. So moving into this new unit, which is called applications of vectors, we're going to be looking at one of the most important, maybe the most important application of vectors in physics, certainly in physics at a high school and through most of university, which is the idea of vectors as forces or forces as vectors. I'm not sure which is the more appropriate way to discuss it. So just like any other vector, a force has both a magnitude and direction. So we should be treating it like a vector quantity. In very simple terms, a force is a push or a pull interaction on an object. And there are a number of interactions that you probably have some experience with, far more than I'm listing here. But some simple ones that I want you to be able to get your head around right away. For example, pushing on a box or pulling on a rope. Those are a couple of very physical interactions that we can imagine. The fact that gravity is pulling you to the ground, or actually pulling you towards the center of the earth to keep you from just floating away from the ground, that's a force that we should be very familiar with. And even just from science class, not even in high school, in elementary school, or even just fooling around with these sorts of things on your own, if you're, well, someone like me, um, then the idea of magnets, the north poles of magnets, if you try to push them together, they'll repel each other or attracting each other. Pushing on a box or pulling on a rope, those are contact forces. We're actually exerting that force through physical contact, whereas gravity and magnets, those are forces that are acting at a distance. They don't require contact to act on the objects that they are acting upon. So that's also something to keep in mind. But the way they act as forces and the fact that those forces are vectors does not change. So if we're going to represent forces as vectors, we're going to make use of many of the same skills and properties that we've made use of so far. So if we start off once again with our force vector, we can, we can break that into a triangle. And in this case, I've broken up that triangle, one part of that triangle along the x-axis and one part along the y-axis. And this is the exact same sort of thing I did when I was breaking a vector into its components or breaking a vector into the basis vectors. As you can see, this blue vector, well, that's along the positive x direction. That's in the same direction as the I vector. And then here we have a component that's in the same direction as the j vector. So you need to continue to think about the force vectors in this way. You can break them up this way. When it comes to figuring out the size of these, and this is one of the big departures from the work we did before, because in general now, the work we did before, we were quite often given different vectors to add together, and then we were trying to find the sum total of those vectors. But now you are quite often going to be given vectors that are, they're going to be in these kind of awkward angles, and it's going to be easier to work with them if we work with them from a component perspective. So the first thing we need to be able to do is figure out, well, how big are these sides? Now, fortunately, that's relying on mathematics that goes back at least to grade 11 and probably to grade 10, which is just using your right angle trigonometry. So in this case, for this force F, the length of that force vector, that's the hypotenuse. Where I have drawn the angle theta, In this case, the angle theta is adjacent to the x-axis, which means that the magnitude of the force vector along the x-axis is going to be related to cosine theta, and the magnitude of the force vector along the y-axis is going to be related to sine theta. And that's because we have the adjacent side and the opposite side when it comes to our right angle trigonometry. So let's take a quick look at an example here. So what we have is a child being pulled on a toboggan. I've got a little snapshot to the right there. And a force of 70 newtons is being exerted along the rope. So newtons are the units that we use to express a force. There are other units that can be used, but newtons are the Système International units that we use for a force. And in this particular case, we're saying that it makes an angle of 25 degrees with the horizontal, or with the ground. So always a good idea, if possible, to sketch the situation. And so what I have is I've got the child plus toboggan, which I'm just going to represent as kind of a box. And I'm going to draw, and I'm just going to freehand it. I'm going to draw my 70 Newton force, and that 70 Newton force is making an angle of 25 degrees with the ground. And so from here, what I'm going to do is I'm going to try to figure out what are the components involved. What are the components in the x direction and the y direction? Now to do that, and this is really a very important thing to do now that we're kind of getting into the application side of things, it's important for us to define where is our x direction and where is our y direction, because it matters when it comes to understanding what do positive and negative numbers mean as we're working through this. So what I recommend is do your sketch, and then in some separate part you might define your x and y axes. And if you draw it like this, it is understood that wherever you've labeled the x is the positive x and the positive y. If you really want to, you could make it very explicit and say that positive x is there, positive y is there. If you're not doing a diagram, then you would probably, I would recommend you do some sort of statement in your work where you say the positive x direction is to the right, or the positive x direction is to the left, or up the ramp, or down the ramp, or something along those lines. So now that we've done this, we know that to the right is the positive x direction. I'm going to form a right angled triangle, and I'm going to find how long each of the sides of this triangle are. And so in this case, this is going to be my x direction vector, and this is going to be my y direction component, or vector component. And now there's a couple of things that I might as well point these out while the examples are simple, which is, the first thing is I can calculate the magnitude of my x component vector. And the magnitude of my x component vector is the magnitude of the overall force multiplied by the magnitude of the cosine of the angle between them. And in this case, it's the cosine because of this angle is adjacent to the x-axis. So that works out to be the magnitude of, well, the magnitude of the force is 70, and then we've got the cosine of the angle. You might say, well, why do you still have the absolute value sign? It's because I'm calculating the size of this side. And if the angle was an angle bigger than 90 degrees, I actually might get a negative result, or I would get a negative result. So I don't want that. So one thing I can do here is I can just go ahead and I can say, I'm going to, sorry, I've just lost track of where I was in my notes. I'm going to calculate this and just look for the side of the angle, or the side of the triangle. And in this case, I end up with a value of 63.4 when I do the math. And then I could say that the magnitude of the force vector in the y direction is equal to the magnitude of the force vector times the sine of theta, and that's equal to the magnitude of 70 sine of 25 degrees, and that one works out to be approximately 29.6. So that's one thing I could do. And now I have found the size of these, and that's perfectly good. Notice I have not included units anywhere. If you want to include units, you can, but then you have to include units throughout. So I could have put a newtons here, and then I could have expressed my answer in newtons right away. Whereas the way I've done it right now, I actually do need to write a concluding statement. But it does want to know what are the vertical and horizontal components of the force. Now I went to the trouble of declaring that the to the right was positive and up was positive. So it turns out that this force in the x direction is also to the right, so it's positive, and this force in the y direction is also up, so it's positive. So now if I were to say a concluding statement, and you don't always have to do these in words, my concluding statement is going to be I'm actually going to write the vector components. Therefore, the force in the x direction is equal to 63.4 newtons, and I'm going to say to the right, and the force in the y direction is equal to 29.6 newtons. Now is when the unit should come back in, and my direction is up. And this is based on the diagram that I've given. Now, I mentioned there was something else that I might want to look at, or I said because this is a fairly simple problem, I want to discuss this, and I don't want to spend too much time on it. But there's another way that we can do this, which is we can say that, and you'll see this among the people who are more familiar with physics, sometimes you'll see people write this, which is they'll say, oh, f of x, and they would probably just go straight to this. They would just go to 70 cosine of 25 degrees. And it turns out that this is still 63.4. And over here, f of y is equal to 70 sine 25 degrees, and it works out to be 29.6, which are exactly the same results as we've got before. The difference is I don't have any absolute value signs, and someone actually asked me this. They said, well, is this the same? When I drop the absolute value and drop the vector at the same sign, is this the same thing? And the answer to that is no. And so that's why I want to point this out to you in case you see it, in case you're talking to a classmate, or in case you actually have your own experiences with this from physics class. These values, if you write it this way, okay, so these can be plus or minus depending on direction. And that there's nothing wrong with that. There's nothing wrong with this notation. There's nothing wrong with doing it that way. I don't know how much you're going to see this in your math textbook. But the reason why these can be positive or negative, it has to do with the angles that we're working with here. And just to give you an illustration, what if we were here, but what if one of our vectors was actually all the way over here? This angle could actually result in both the sine and cosine giving negative results. So this is where having a diagram comes in as being so important, because if you've done a good diagram, you're going to recognize this anyway, and maybe you will work in terms of, which we often do, maybe you will work in terms of the related acute angle, but you'll still understand that if this is your positive x and if this is your positive y, then you're going to get a negative x component and a negative y component. Some other things for you to think about while you're digesting what I gave you on that previous page is there's some terminology that you need to be able to work with if you're going to do this work dealing with forces as vectors. One of them is one that we've been making use of, which is this word resultant. A resultant vector is when you do a vector sum. A resultant force is when you do a vector sum. It's just what are you doing the vector sum of. So when you do a vector sum of all forces, you end up with the resultant vector, which we generally denote as F sub r. I will sometimes refer to the net force, and certainly people with a physics background, I'm not sure if you'll see this in your textbook, but the net force and the resultant force are the exact same thing. They're interchangeable. Forces tend to, for lack of a more precise word for now, I'm going to say tend to move objects. Now, in physics, it actually has a deeper meaning than that, and we have to be more specific. But in a very rough, because we're not teaching physics here, a very rough explanation is just let's think of forces as wanting to move an object. So the easiest way to think of equilibrium is an object that is not moving. Now, equilibrium can occur under other circumstances, but we don't need to get into it to appreciate the vector side of things. So equilibrium is when the sum of all forces is zero. And one very common way to see equilibrium is when you have an object that is completely at rest, that is not moving, then all of the forces acting on that object add up to be zero, or the zero vector. In other cases, you will actually have a resultant force that's non-zero. So it's going to cause the object to move in some way. And you might be asked to discover or define the equilibrant force. And that's the force that would actually prevent the motion from happening. And that's just the opposite. That's the opposite vector to your resultant vector. So the equilibrant force is just the negative of the resultant force. Now, there's more that I want to go through here. I have some more examples that I want to do, but this video will get too long otherwise. So I'm actually going to break this in two parts. The other thing is there are a number of students who will have the required background in physics to go to this homework immediately, and they can start working on that right now. If you do have a physics background, please try to represent your work in a way that's consistent with what I'm showing you here in the course. And if you're not sure, of course, you can go ahead and ask. I'm going to make another video where I'm going to go through a few more examples. They are examples that are also in the textbook, so you can also take a look at this chapter in the textbook if you want to just read through those examples and see those.